today we have Reza Shokri, who's joining us from Singapore. We're at 7 a.m. and he's going to be telling us about some of his latest work on membership inference attacks, which is a topic that he has done a lot of work in, including coining the term. So this should be very interesting.
Hello, everyone. It's great to be with you. Thanks for inviting me. And this is very exciting, given that there are many experts in this field on inference attacks and privacy auditing in the audience as well. But I'm going to focus on what we have been doing very recently with my great co-authors, Sajjad and Philip, in this paper, Low-Cost, High-Power Membership Inference Attacks. And I'm going to give a little bit of background, given that I don't know who exactly knows how much about the entire field of membership inference attacks, and also given that this is going to be recorded and released online. But this talk is not a survey on all the existing methods in membership inference attacks. So if you have some data which is very sensitive and normally you don't release the data, if you train a model on it or you compute high dimensional statistics on the data, you should be also worried reasonably about whether releasing that would endanger privacy of the individuals who contributed to the original data set. And if you have this valid concern, we need to have a definition for what that concern is. What is the privacy risk and the notion of information leakage? And specifically for the case of training and releasing a model, we are interested in measuring if an adversary, by observing a released model, would be able to distinguish between what data was used for training the model versus the rest of the population, right? Why? Because if this happens, essentially we enable the adversary to learn something about the training data that would have remained private to him without observing data. And if the adversary is able to do that, to extract that information, eventually, if the leakage is high, would be able to also reconstruct the data set, at least partial. So that is the notion of privacy risk that we have in mind. And this gives birth to the membership inference attacks and motivates them. What is membership inference attack? Given a model theta and a data point X, we want to know whether X was part of the training set of data. It's a binary decision-making process. So in order to formalize this and construct a framework for evaluating information leakage based on membership inference attacks, similar to what we do in cryptography, we construct some form of indistinguishability games, which we call membership inference games. So this is between two parties, the challenger and adversary. The challenger, in the typical case of designing these membership inference games, the challenger would choose a data set. In the worst case scenario, the adversary would choose the data. But then given that data, the challenger decides to include one particular data point in the data set when it trains a model on it, or exclude it from the data set, right? So here, without loss of generality, D0 or D1, one of them is going to be included in the data set and the other one will be excluded. D0 would be the challenging data point X. So this X and theta would be released and shared to the adversary, and the adversary runs an inference attack and determines whether essentially that data point X was included or not. He wins if the guess is correct. Okay, so this is one instantiation of the game. And what we do is that we run this experiment many times, and we measure on average how many times the adversary would guess the members and non-members correctly. as in the case of many other binary decision-making processes and also hypothesis testing, binary hypothesis testing frameworks, we measure the true positive rate, which indicates how effectively the adversary is able to recover and identify the training data. And then his false positive rate, which roughly speaking is the level of anonymity that every identified training data has, right? So the adversary might be able to identify data point X being the member, but he's also confusing the membership of many other non-member data points. That gives some level of protection to X. So there are these two aspects that we need to be able to evaluate. So for a given specific fixed attack, then we have a point in the power versus error, TPR versus FPR of a membership inference attack. And of course, here, this is one single attack. I'm not specifying how exactly we came up with this attack, but you would say, well, if you have higher power for lower error, then that means there's more leakage, right? So to design an attack method, I'm going to formalize the general approach that we can have here, because we are designing a statistical test for this hypothesis testing problem. And what we can do is to compute some test statistic. We call it score MIA, which is a function of the data point X and the model theta. And this score MIA is going to essentially help us to order any data in the universe based on which one is more probable to be in the training set. And having this, we decide if a data point is a member if that score is larger than some threshold T. Okay, so this is how we compute the test statistic, and then we turn it into a binary value member or non-member. Now, given this general framework, every data point in the universe, the ones that are in the training set or in the population, would be mapped into this one-dimensional space according to this score. And then wherever you put this threshold, whatever is on the right side of it would be, according to that attack, labeled as member. So here we have the red data, for example, as the training members of the training set, and the rest are the rest of the population. So wherever you put the threshold, then you will see that the adversary is going to recover some of the training data, but he's going to make some false positive error as well. But the threshold could be anywhere, right? Depending on how much coverage the adversary wants to get, right? So the adversary can put a threshold quite in the middle and then recover a lot of the training data, but also incur some error. Or the adversary could be very conservative and say, I want to recover a very few data points, but be sure that I'm not confusing them with the other data from the population. If you vary that threshold from in different points in that spectrum, then you get many attacks. Essentially, every threshold corresponds to one single attack. So we have many attacks. And if you evaluate the TPR, FPR for all these attacks, it gives us this curve. So these curves give us a full picture of information leakage in an algorithm, according to this methodology. The closer these points or the curve is on the to the top left corner of this diagram, essentially it indicates that there is more leakage. The lower it is, the closer it is to the x equal to y, it indicates that there is less leakage. However, this reveals or evaluates the leakage according to a particular test statistic that we computed according to a particular membership inference attack. So if you want to have a more realistic evaluation of the risk of an algorithm, we want to design stronger attacks. So to get closer and closer to the true leakage of an algorithm. So if you want to choose the threshold, because earlier I mentioned that the threshold could be anywhere, but how do I choose the threshold, right? One way is to just say, well, I'm not running the test. I'm not simulating an attack. I'm just going through all possible thresholds and scan the entire spectrum and basically draw this curve. Okay, that's a possibility if you just want to do an auditing, essentially. But if you're an adversary, you have to choose a particular threshold because you're running one attack, right? So how do you choose that threshold? You choose it depending on how much error you're willing to tolerate, right? So if the adversary is willing to tolerate alpha error, FPR, then he would say, well, if I choose a particular threshold T in the null hypothesis setting, in the setting where X's are coming from the population, that would result in a particular level, a level of error. I would choose T such that that level of error is alpha. So T is essentially the inverse of the CDF of that score me under the null hypothesis. So that's a broad description of what the attack is and how to construct it in a very general framework. And every attack that is designed so far and we have been following in the literature could be somehow represented in that framework. So there has been, over the last maybe 15 years or so, there have been many interesting tests from the time that the Homer et al. Essentially introduced the first membership inference attack. Also in the original differential privacy paper, there was a discussion about semantics of differential privacy and connection of that to inference attacks. The tests got better with the work of Sankararaman et al. And then there are many more interesting works that followed from there. What I'm going to talk about is an attack that we just constructed. We call it ARMIA. R stands for robust, and it becomes more clear why we call it a robust test. So what do we want to do? We want to design a hypothesis test. We want to distinguish between the cases where X was actually part of the training set of theta and the null hypothesis. So a test would be a more powerful one if it would be able to reject the null hypothesis more accurately, right? And this requires us to have a very precise model of the null hypothesis. What is a null hypothesis? All the possible worlds in which X is not part of the training set of theta. All possible worlds where X was not chosen by the random secret bit of the challenger. So here is our main idea, and then this is the construction of ARMIA, that instead of assuming one single world, one average case null hypothesis, we decompose it and say that, well, if X was not part of the training set of theta, some other data points were replacing X, perhaps, And so it could be that if X was not chosen, some other data point Z was chosen instead of X, where that Z data point, that alternative point, was essentially sampled from the population. So we designed this pairwise likelihood ratio test, which tells us which one is more likely, the world in which I observe theta given that X and a number of random samples from the population were used to train model, or the world in which I observe theta and Z and a bunch of other data points were selected for the training of the model. So if I have this test, it would just say which one is more probable relative, the presence of X in the training data relative to the presence of Z. Here, the probability of theta given X is computed over the randomness of the algorithm. And this is essentially, P of theta given data D is essentially what we optimize when we want to train a model or learn some statistical model. So having this pairwise test, which represents the comparison of the two worlds given one instantiation of the null hypothesis, we expand it to the entire space of the null hypothesis, which Z could be any sample. So then we construct the test statistic, the score MIA, as the fraction of the population that X would dominate using this likelihood ratio test. So where it stands in the distribution of this population data, the distribution of the pairwise likelihood ratio computed for population data. So that's essentially our test, right? Very simple and hopefully very intuitive. So we need to compute these likelihood ratios. And the way that we compute it, we just use the Bayes rule very simply to expand these terms. And the P of theta would cancel out. Essentially, what remains is the probability of X given theta over probability of X, and the same for Z. So what is probability of X given theta? Is the probability that the model would produce X correctly given theta in the classification task, which is what we are going to evaluate later. This would be the probability that the label for X is correctly predicted given its features, and which is a softmax. And P of X is essentially the normalizing factor for that Bayes formula, which we can compute empirically. But here, when we expand this P of X, which we have to go through all possible models, and then the data that was used to train those models, we need to have access to some theta primes, which we call reference models. These are the models that usually in the literature researchers use to construct their membership inference attacks. There are some details on how to choose them because we cannot essentially integrate over all possible theta primes. We have to sample from this space, and there are some details that I omit here. We can discuss after the talk on how to do this precisely. But assume that I have those models that are trained, and using that I compute P of X as well. So essentially I have everything that I want. I have some reference models that would enable me to compute P of X and P of Z. And I have the target model theta that enables me to compute the P of X given theta. So that's all. If I put everything together, essentially, as I said, what I want to do is to know if this P of X given theta over P of X is larger than what fraction of the population, right? And if I want to visualize it here, if you assume that this Gaussian curve, which by the way, the distribution of P of Z given theta over P of Z is not Gaussian, but I just use this to illustrate my point. If you have this distribution, then if you put the threshold on the 1 minus alpha percentile of that, you get alpha percentage FPR. So the test, if you want to achieve alpha FPR, is to compare the MIA score with 1 minus alpha. Very straightforward. So this immediately would give you a test for every FPR that you are interested in. So that's the entire motivation and construction of the test. Let us go through some evaluations. If there are some questions about the construction of the test, maybe this is a good time as well. Otherwise, I can just continue.
Yeah, one quick question maybe. So when you pick the example Z, you just pick it randomly from the data distribution?
Yes, yes.
Okay. And you do this averaged over many other examples Z?
Yeah, it's not an average, it's the kind of the percentile, yeah.
Okay.
Where you stand compared to all the Z points.
Yeah, okay. To all the other ones, so you compare it with respect to every other training point?
No, not every other training point. So Z is a random sample from the population.
Yeah, okay, sorry. And how many of these random samples, like, are you taking? Trying like to get as many as possible from the population, or like 10 or 100, or I don't know?
Oh yeah. So in practice, essentially, let me say that relative to how much data you need to train, for example, the model itself, right? So if you have the data points, the model that is trained on 25,000 data points, I think we used, if you use 1/100th of it, you get a very good TPR.
Okay, that's very small. Okay, yeah, thanks.
Yeah, but if you increase it, of course, you know,
the diminishing, but the diminishing returns around 100 seems reasonable. Okay, thanks.
Yeah, that gives you a reasonable test. Yeah.
So just to be clear, the probability of X given theta, that's basically the loss, right?
It's proportional to e to the power of minus loss. Yeah.
Okay.
Yes. Yeah. So if you use cross entropy loss, essentially that's e to the power of minus loss becomes the probability of correctly predicting the label. Yeah.
Okay.
Any other questions? So let's go through evaluating this. The evaluation is pretty standard in the sense that especially the field has become very mature in the last few years. And there are some data sets and model architectures and so on and so forth that everyone is using. So we are just running the attacks on the same benchmark data sets and benchmark models. Here I focus on classification tasks. So the first question that I'm asking here, because having a low-cost test was one of our major objectives, is how many reference models you need when you compute the score MIA for our attack versus the other ones for achieving a certain level of test accuracy. Right? So here I show AUC, but then I'll show the details as well. So as you'll see, if you have a single reference model, many other attacks. If you have few reference models, many other attacks. would not be able to achieve a good level of AUC. But our attack would perform very close to the maximum test accuracy, or at least the empirical test accuracy obtained by any test, and close to maximum with even one reference model. Right? So this means that let's say you have a model, you fine-tune it, you don't need any other model. You can just immediately audit the model using the pre-trained model. If there are some models trained, a few models trained by others, you can use them without the need to train more models. But of course, if you want to get the maximum performance of the test, increasing the models, the number of reference models would help. Some tests are interesting, but they would not benefit from more training, but some others, they do. There is an interesting setup in the literature, most notably by the work of Nicholas and others, that distinguish between two settings. Essentially, the setting where these reference models could be trained as a function of the target data points. So you include the data point in the training set of those reference models, and you make essentially the reference models dependent on the query, and this is called the online attacks, so online setting. And there are other models which are trained independently from what data point you're going to attack now. So these are the models that will be used in the offline setting, right? So the online setting essentially uses both kind of models. The offline setting only you use the models that are trained independently from what you're going to attack later. So these online attacks, especially for the prior work Lyra, would help a lot. And we also have a version of our attack that uses the reference models dependent on data points. But I want to use these kind of attacks as proof of concepts. They're very powerful, but in practice, we would not be able to use them if you want to do auditing on large models, or if you are an adversary that wants to use, let's say, membership inference attacks as an oracle for reconstruction attacks. In that setting, you would not know which query you are going to test. So, but we compare with them, we want to compare with the strong attacks. As you see here, the Armia is showing a very good performance and dominates others. But something which everyone is interested in is the entire ROC curve, right? Not just the area under the curve, but the entire ROC curve. So we need to look at the TPR at different FPR values. One part of that, which is very challenging, is to increase the TPR when the FPR is very small, and we challenge this attack and others at FPR 0 as well. So depending on how many reference models are needed to be trained, we'll see that essentially this Armia test would dominate all the other tests, whether they're online or offline, regardless of how many models are being trained.
How do you have a 0 false positive rate?
So 0 false positive rate, essentially in the percentile that I showed you for the attack, if the threshold is after.
Oh, so like 0 empirical, but like there'd still be some.
Yeah, zero empirical. Yes.
Okay.
Yeah, I mean, these are all the evaluations here are empirical tests, right? And any other question here? So some of the attacks, for example, if you only use the population data exclusively, or you only use loss and sweep over it. They don't use any reference model. There's this recent quantile regression method that doesn't use reference models, but it does train some attack models. And the rest of the attacks, the strong attacks, essentially require training reference models in the way that the target model is trained. Some other setting that we want to challenge the inference attacks is the setting where non-members are not in distribution data. So if you have non-members that are out of distribution, which is the case notably if we use membership inference attack as an oracle in reconstruction attacks. So how do we do reconstruction attacks? At least one way to do it is to just go over all possible data in the universe and then select the ones that you think are members and then claim that that's the reconstruction of the data set. Or you can have a smarter way of sampling instead of going through the entire universe. But essentially, many of the data points that you test are out of distribution. It's very important to have a high true positive rate for low false positive rate in that setting when the OODs are the main bulk of your non-members. So in that particular setting, which by the way deviates from the membership inference game that we discussed before, and this is one way to test the robustness of membership inference attacks. If we do so, we'll see that our MIA performs very well compared to the other tests that would have a very low TPR in those settings. So this is a scenario that I think we all need to look into better to see how we can design tests that would be able to differentiate between members and non-members if we don't completely follow the assumptions made in the membership inference game. So if I want to summarize the empirical results that we have, and you can find all the details of the tables and ROC curves, etc., in the paper, which we'll also update soon with more results. Armia outperforms all attacks in the sense that the TPR FPR curve that we get for Armia dominates the curves obtained from other methods across all FPR values. And can achieve close to its maximum power, even if we train very few reference models. So this is very impressive. The main reason why I think this is achieved is that we have a more precise modeling of the null hypothesis. And other attacks could be somehow modeled as uncalibrated or average versions of our attack. So I'm not going to be very formal here, but let's go through some of these. So for example, attack P here, which is the evaluating where the loss of a model is in the distribution of loss of population data, or the probability of the data in the distribution of probability of population data. It's uncalibrated with respect to the distance between X and Z in the distribution of models, because here we only look at the distance between X and Z when we only look at theta, whereas Armia looks at that and compares it with how far X and Z are with respect to the reference models. Inversely, when we look at the reference models in attack R, and we measure where we calculate where the probability of a data points on a model theta is within the distribution of X given reference models, we are not calibrating this distance with how far X theta and theta prime are with respect to some other population data set. And for the case of Lyra, in its offline setting, it's close in nature to attack R, but in its online setting, essentially the null hypothesis setting is averaged. The probability that I observed theta, given that X was there, compared to the case where it was not there, but I'm not distinguishing between all the possibilities. So this would give the power to RMIA. Another detail here is that when we look at the computation of the score MIA in RMIA, we can have a direct way of computing P of theta given X over P of theta given Z in the same way as is done in Lyra by approximating the distribution of the output of the model over all the models trained on it, etc. But it turns out that direct way of computing the likelihood ratio requires many models to converge on an unbiased estimation of that probability. Whereas when we do the base computation of it, we don't really need that many reference models. So there's that as well. But if you look at just how we differentiate between the in and out worlds, by decomposing the hypothesis testing problem, we allow a more precise test. So if I want to conclude, there are two scenarios in which membership inference attacks are important and are being used. One is for auditing. In this setting, it is crucial that the membership inference attacks are low cost. And essentially, this is a very important and practical problem that we need to solve, but we should not sacrifice the power of those tests where we design low-cost auditing techniques. A challenge, for example, would be that we have a single reference model, and I think I encourage the researchers to think about how, with a single reference model, we would be able to improve the power of the test. And MIA is also used as part of the attacks. And in this scenario, essentially, we should not evaluate MIA under the assumption that everything is correct and precise according to the membership inference game. So there could be deviations from it, right? What the adversary assumes is used in terms of the selection of the data or training of the model could be deviated. And we need to test how robust these membership inference attacks are when we add some randomness to that process, right? So the test against out of distribution data was something that in particular I showed you here, but you can also imagine that the data that the adversary has doesn't follow the same distribution. The population data distribution is unknown to adversary, etc. So that's all, and I look forward to more discussions with you. And essentially, this work was inspired by looking at many prior works that tried to improve the power of attack. Again, I want to emphasize that if somebody wants to is listening to this and wants to learn more about how to design membership inference attacks in a in a rigorous manner, they have to start from reading the Sankara-Raman et al. Paper, which was essentially written right after or around the same time as Homer et al. Paper, and then get into the membership inference attacks in machine learning. So thanks a lot, and look forward to more discussions.